Hello everyone, and welcome to today's webinar on Control Optimization System for Water-Cooled Chiller Plants. Before we get started, I wanted to go over a few webinar logistics. Hearing that there's an echo issue, can everyone, all the presenters, I think everyone should be muted, but make sure that we have all the other lines muted. So today's webinar will discuss the testbed evaluation by the Pacific Northwest National Laboratory. And this complete report, as well as a one-page infographic and a four-page findings, are available on the GSA website at gsa.gov/GPG. And can someone chat and let me know if there's still an echo issue or if that's been resolved? Okay, sounds good. Today's webinar is one in a series. The upcoming webinars include a webinar on July 13th on condensing boilers. In August, we'll be hosting a webinar on synchronous and cogged fan belts. And September 14th will be a webinar on next generation chillers. And you can access recordings of all past webinars also at gsa.gov/GPG, and you can also see the schedule of upcoming webinars here as well. Many of you are already using the chat, which is great. So this is today's broadcast is listen only, and you can submit questions in the chat box here on the right side of your screen. And you don't need to wait until the Q&A session, which will happen at the end of the session, at the end of the presentation. In fact, we're encouraging you to submit your questions well in advance of the Q&A. And now, today's webinar will cover an overview of GPG from Mike Lowell, a GPG program manager, followed by the presentation of the testbed assessment by Ron Underhill of Pacific Northwest National Laboratory. And then we'll hear some on-the-ground feedback from Mark Moody and John Teagan, and this will all be followed by a Q&A facilitated by Mike Lowell. And now, Mike, would you like to introduce the GSA Proving Ground program?
You bet. Can everyone hear me? Andrea?
Yes, we can hear you.
Okay, good. Hello, everyone. Welcome to today's webinar on a control optimization system for chiller plants, the third in GPG's Outbrief series. As Andrea said, my name is Mike Lowell, and I'm a project manager with the GSA Proving Ground. I will be facilitating today's presentation. The GPG program enables GSA to make sound investment decisions in next generation building technologies based on the real world performance. By discovering best of breed innovative technologies early in their development and place them strategically within our federal properties, we help ensure GSA's leadership position within the commercial building industry. Since its ascension in 2011, the GPG program has evaluated dozens of next-generation building technologies in real-world operational settings, recommending the most promising for deployment within GSA's real estate portfolio. We identify promising technologies at the edge of commercialization. Note that tested technologies are not available at your local hardware store. On average, we receive 80 applications each year, and we pick typically around 5 to test. Once technologies are selected, we partner with highly respected DOE national laboratories to objectively evaluate real-world performance. To be recommended for broad deployment, technologies need to meet all of our success criteria for installation, performance, and maintenance, and they need to be cost-effective. There's tremendous innovation going on, and we are constantly being challenged to do more with less. Innovation is what drives the efficiencies that let us achieve that, especially given that we in the government at least have picked the low-hanging fruit. But looking at this graph, which shows kind of the life cycle, if you will, of new technologies, 4 out of 5 technologies never cross the technology valley of death. They may go through the R&D process, but getting across that valley of death from R&D to commercial maturity and success is very difficult. GPG helps bridge that gap by leveraging the scale of federal government's portfolio of office space. We're the largest single commercial building owner to do research required to vet innovative next generation technologies. As a side note, the majority of our GPG technologies that apply for this program and get selected come from the middle of this graph, those pre-commercial, early commercial technologies. So we're kind of a springboard for them. We have two other public programs that GPG coordinates with. DOE's Better Buildings program, and they focus on the uptake of these next generation technologies with private sector commercial building owners, and a sister program to GPG at the Department of Defense, which proves out next generation technologies applicable to onshore military facilities. GSA tested today's technology in Montgomery, Alabama, and has since deployed in other locations throughout the country, and here's a list of some of those locations. Now Ron Underhill will discuss the evaluation of control optimization system for water-cooled chiller plants. Ron comes from Pacific Northwest Laboratories. Thank you.
Thank you, Mike. Can everyone hear me okay? I'm pleased to be...
Yes, we can hear you, Ron.
I'm pleased to be presenting for the Pacific Northwest National Lab on the Siemens demand flow technology, and this does have a vendor behind it. There are multiple vendor technologies out there, but this happens to be the vendor of choice right now, at least for the demand flow. And so the next few slides, we're going to discuss how the National Lab measured and validated some of the aspects of this technology. On the current slide, there's just a short description of some of the challenges that are being faced by chill water plants in commercial buildings. And this particular slide, let's just stay here for a second. This slide shows typical commercial building optimization issues that are currently encountered are the dance, if you will, the synchronization of multiple components, towers, tower fans, condenser water pumps, chill water pumps, and then it gets even more complex if your system is a primary, secondary, where you have pumping systems that are pumping out to the buildings. And this is a very simplified diagram of the site at Montgomery, Alabama that we're going to be talking about. Some of the things that aren't shown in this particular slide are some of the additional sensors and instrumentation that were installed by the vendor. They actually had to do some modifications. They had to add power meters for the towers. The towers had existing VFDs. The primary condenser water pumps and the primary chill water pumps did not have VFDs, so those were added as part of the technology. In addition, there was differential pressure sensors that were put across each of the pumps, both for the condenser water, primary chill water, and secondary chill water pumps, flow meters, and they actually installed quite a few temperature sensors that were higher grade, higher level of accuracy. So the technology is in one sense somewhat out of the box for the software, but in another sense it is customizable per site. And we're only going to speak about this site, but the vendor will do an evaluation of your site and look at your different contingencies, your different design anomalies, and then from that analysis determine what additional components need to be added. In some cases, if they do not see isolation valves, in this particular site they did add isolation valves for the cooling towers. Again, the optimization strategy for this particular technology is to optimize flow. So we're particularly talking about pumps and the flow rates through the towers, through the condenser bundle, through the evaporator, and even extending out to the building to the air handling unit coils. This particular drawing is simplified again, as I said. We're going to talk in more detail about the particular building, the U.S. Courthouse, the Frank M. Johnson U.S. Courthouse in Montgomery, Alabama. So go ahead and go to the next slide. The opportunity for GSA is significant. I believe this graphic here is accurate. A lot of GSA floor space, pretty much throughout the entire GSA portfolio, requires cooling, whether it's process the majority of which is probably comfort cooling, but nevertheless there is cooling requirements. The question is how long, and is it all year? Is it just for a short summer season, or is it for an extended shoulder season that extends into the fall and starts early in the spring? And that varies, of course, by climate zone. And of course, if there's data centers in the building that either have their own chiller or they tied into the chiller that also provides comfort cooling. So some of those things have to be looked at in greater detail as you explore this type of technology, because it will impact some of the decisions that go into whether or not you would apply this technology. Let's go to the next slide. So we're going to talk about the Frank M. Johnson Jr. Federal Building and U.S. Courthouse located in Montgomery, Alabama. The picture there shows actually two buildings. The building in the upper right corner with the red tile roof was the original site that was constructed in 1932. It was originally a federal building that housed the post office and other federal agencies. And then in 1978, the post office was relocated. And then in 1996, the annex, which is the radial arc building, the lighter color building, that was constructed in 2002, was occupied. So the chill water plant that's housed in the basement of the large arc radial building serves both buildings. And so the previous slide that we looked at actually has two sets of secondary pumps that distribute chilled water to both buildings. The challenge is the annex, which is the original building, the red tile roof, was never designed with any airside economizers, and so therefore often requires cooling almost year round. And the challenge that brings is low loads for a lot of chill water plants that are constant flow have a very difficult time maintaining consistent or efficient operation. So those are some of the things, background. Historically, this is a site that has a lot of history because of the civil rights movement. Not far from this site was where the Freedom March and the Montgomery bus station mob attack occurred, and there's been some major decisions that occurred here. So historically a very significant site. The chill water plant consists of three 400-ton constant speed centrifugal chillers, and as we're going to find out in this discussion, VFDs were applied to everything except for the chillers and the compressor motors that serve the chillers. Let's go to the next slide, please. So part of the measurement and verification that occurred by the National Lab over an eight-month period from January 2013 through September of 2013 was based on how the system was designed with the variable speed pumping operations, the variable speed tower fan operations. And as you can see in the graph, the green box represents on average the savings that was identified through that monitoring period. And some of the things that are of note that would be important to note, the red line represents the average KW based on a simulation period. We had no baseline data for this site. So coming up with a baseline data was a little bit challenging. We had 2 weeks in March of 2013 and 2 weeks in September where we configured the plant to be basically a constant volume operation. Now, because some things were modified, that required the VFDs to be put at full speed, and some things had been added to the design isolation valves. Those had to be put back in a full open position. Other things were modified in the control code. So it was I would say probably a 90% accurate simulation over a 2-week period in March for a winter simulation, and then 2 weeks in August. And the other thing of note is that the improved software, you can see the blue line is the post data performance, shows an earlier startup in the morning around 5 a.m. And then a slightly higher elevated consumption around 7 a.m., but then a significant decrease throughout the day. And primarily we attribute that to the pump savings. Let's go to the next slide. The number one thing that we saw based on the data and the measurement and verification was that the delta T was consistently maintained above 8 to 10 degrees. I apologize for the wording there. During part load conditions, that should say greater than 10 degrees Fahrenheit consistently, 8 to 10 degrees. So, and the delta T was noted as being as high as 18 degrees. So there's a lot of improvement. Typically, constant volume systems, one of the things that they struggle with in a primary, secondary chill water plant design is low delta T during low load, and even sometimes during greater load. So this was a significant improvement, and it resulted in operational improvements as well. During low loads, as we noted in March, April, wintertime, the operation staff encountered a lot of times when the chillers would cycle off on low loads or other anomalies related to low delta T. Let's go to the next slide, please. And this is some of the data. Again, roughly 35% savings at the chill water plant. This is not whole building savings. And again, this was based on the comparison of the simulated period of 2 weeks in March, 2 weeks in August, to the other 6+ months of optimized performance. So an average of about 0.6465 kW per ton, which is actually very good. You may have some technology already that's doing it as well, but if you have a plant that is struggling to get to that level of performance, this is again on average, and what you see in the graph there is a representation of how the individual chillers performed. We would expect similar performance for each of the chillers. The lines there all show reductions. The gap between the before and after may be based on some maintenance or age issues between the chillers and some operational issues. Let's go to the next slide, please. So again, what we identified based on the average savings was about 7-year payback. What we did not note was this project was funded, I believe, through ARA. It was about a $300,000 capital improvement project, and that funding covered a lot of things that you probably should be aware of. There was obviously some engineering analysis that was done by the vendor. They identified where some 1 or 2 VFDs had to be added. Obviously, the instrumentation that was added. The software, they have a software, proprietary software that they add to the network, the BAS network. In this case, the BAS was already Siemens. The vendor does claim that they can integrate to other vendor systems, and we were not able to validate or verify that. And so we were just focused on this site. Again, based on the savings that we saw, which is about an average, based on the savings we saw, about $42,000 for the chill water plant per year. So that's comes out to be about a 7-year payback at the utility rate of 8 cents a kilowatt hour. If your utility rates are higher, obviously your payback will be sooner, assuming you have similar plant, similar performance. So based on those numbers, the optimum that we came up with would be if you had on average a 6-month cooling season at utility rates greater than or equal to 11 cents a kilowatt hour, then you'd need at least 3 million ton hours a year to be cost effective for this technology to approach that level of payback. If you have lower utility rates, it's going to obviously take longer. So we would recommend, if you don't have 4 million ton hours a year of load or chill water plant performance, then it may take longer to pay this back. So those are some things to keep in mind when you start looking at, is this technology something that I should consider for my site? Let's go to the next slide, please. And just some things that we noted based on the performance. The cooling tower, condenser water entering condenser water temperature never was operated any lower than 65 degrees. Obviously, in this climate location, the higher wet bulb temperatures have some impact. During the summer months, you're never going to get down to 65 degrees anyway. So, but there were times in the cooler months when they could have attained lower condenser water temperatures, but the software, for whatever reason, did not do that. We also, I don't know if this site was set up to do any water side economizing. As I said earlier, the original building did not have air side economizing, and that's something that may or may not be of concern. But this site, if it had a water side economizer, we were not aware of it. Chill water set points, the vendor, one of the things that they don't really, they do adjust the set point, but they actually, in their literature, will emphasize that by optimizing the flow rates through the chiller, evaporator, and the condenser, and trying to synchronize that so that there's no low delta T issues, which they were able to do successfully. You're getting the proper flow rates through the chiller and then out to the building on your secondary loops. By doing that, they would actually recommend possibly running lower chill water temperatures, which in a lot of parts of the country are necessary for humidification control or dehumidification, and yet do that in a way that it not only allows you to dehumidify, but even run your VAV systems in such a manner that you ensure that you're not paying a penalty with potentially higher static pressures, or not able to maintain static pressure, I should say, due to VAV boxes not being satisfied. And then some of the other things that are not on the slide that you might want to consider is the things that we saw that were improved were staging of chillers. Again, if you have 2 or more chillers, the ability to run only 1 chiller. Some of the newer chiller vendors, however, will say that they want to see you run 2 chillers because their optimum kW per ton performance might be where they're 50% or less loaded. So all those things need to be taken into consideration, and obviously the vendor would look at all that and make sure that they're optimizing staging of chillers. So let's go to the next slide, please. So some of the deployment opportunities that we looked at were, again, we've noted earlier, 3 million ton hours a year or greater, depending on your utility rates. If you have low utility rates, then you may be pushed into 4 million ton hours or higher scenario. So obviously, when we looked at the list of sites that were listed earlier, what I noted was Midwest and Southeast locations in the country. I'm not saying that if you're in a different climate zone that this technology wouldn't apply to you. You may have other loads that would be driven based on data center or process cooling that might be advantageous for this type of technology. Some of the things that, again, I would recommend that you become aware of as you look at applying this technology is my building, does it have a BAS that is amenable to their technology? Will it integrate? Do I already have plans to upgrade my chill water plant? Their costs will come down if you already have VFDs, if you already have the proper instrumentation, if your system is already configured with 2-way valves versus 3-way valves. So some of those things will impact the design and cost. And again, this is a customizable solution per site. So those are some of the things that you need to take into consideration, and obviously have the vendor provide an analysis if it makes sense. You may even want to have them guarantee the savings. So there's some kind of a performance guarantee there as well. So if you're looking at this, I think you could back calculate it out. We did real quickly. If on average you have 500 ton hours a year of load, 500 ton hours and a 12-hour day and a 5-day week, you would probably need to have a chill water plant that ran 100 days or about 20 weeks out of the year for it to have some kind of a payback that would push you over into saying, okay, this technology probably has application for us. And anyway, so I think that's pretty much all that I have to present right now, and we'll look forward to any questions that might come at the end of the presentation.
Hi, this is Mark Moody, mechanical engineer, Energy Branch, Facilities Management Division, Region 4. Can everybody hear me okay? Okay. We had 3 goals for installing demand flow at the FMJ complex. First, lower central cooling plant electrical energy usage, thereby reducing the building's energy use intensity, or EUI. Second, improve the chill water plant's cooling turndown capability in order to provide year-round cooling. This should help improve tenant comfort and help resolve some tenant complaints we were having. And third, provide greater visibility into the central plant equipment via the building automation system. This should help improve system monitoring and troubleshooting. Next. For goal number 1, Ron discussed the pre- and post-installation power comparison and the improved efficiency of each chiller across its load profile. And he talked a little bit about some of the sequences that demand flow tries to optimize. And I want to go into a couple of other particulars about how demand flow works. First, demand flow optimizes the chill water and condenser water temperature set points and chill water flow rates based on current system conditions. The plant sees improved efficiencies at different combinations of condenser water and chill water temperatures and chiller loading. This is integral to how the demand flow algorithm increases cooling plant efficiency. Next, demand flow improves chiller sequencing so as to increase chiller runtime at higher efficiencies. That's because chiller efficiency changes based on the amount of chiller loading. Demand flow tries to increase the runtime at these higher chiller efficiencies. Next, demand flow improves the cooling tower fan sequencing. For example, 2 fans are energized at part load rather than 1 at full load, and that's more efficient. And lastly, we submeter electrical usage to provide demand flow the inputs it needs to make decisions in real time. And as Ron mentioned, we have quite a few variable speed drops that we added, primary and secondary chill water pumps, condenser water pumps, tower fans, and of course temperature sensors. Some of those were new, some were not new. We just had to replace them. And then lastly, current transducers for chiller compressor motor and pump motors. Goal number 2 was to provide the ability to cool the FMJ building all year. Prior to the installation of demand flow, the cooling towers had to be shut off during the winter. They would develop ice in the tower fill if not shut down. So as a result, those parts of the building that needed cooling in the winter would overheat since only the boiler was running. Building management would actually have to open windows to cool back down certain spaces, so the situation caused a lot of extra work for building staff. And of course, there were tenant comfort issues and complaints. After demand flow installation, this issue was resolved. The cooling tower fans now had the ability to throttle down. Condenser water temperatures were reset, and we no longer had the freezing issues at the tower fill. So the mechanical system could now control space and set points as intended under automatic control. Next. Goal number 3, provide greater visibility into the central plant equipment via the BAS so as to improve system monitoring and troubleshooting. On a previous slide, we discussed some of the instrumentation and hardware required for demand flow. Besides improved system performance, another result was new BAS inputs and output points and the ability to perform new trends with all this new data we were receiving. So here we're showing all the new points, status and or control for chill water pumps and pump motors, cooling tower fan speed, and fan KW. And then some of our new capabilities, we could run new trends with the new input-output points. We had the ability to compare one chiller's efficiency in real time to the others. Also, the ability to monitor in real time the central plant KW per ton. And we could monitor real-time equipment KW for pumps and cooling tower fans. Next. So here's a few examples of how the additional BAS points and functionality is useful. First, pump KW is part of the dashboard on the BAS workstation. Each pump's KW is visible on the same screen. We actually had a situation where O&M noticed that one of the pump motors wasn't pulling the same KW as the other pumps. O&M staff determined fairly quickly that the pump had a blown coupling and replaced it. Another example, the efficiency of each chiller is shown on one screen at the BAS workstation as well. O&M can compare one chiller's efficiency in real time to the other chillers, And if it's underperforming, they can inspect the underperforming chiller for deficiencies. And then lastly, the real-time central plant kW per ton value provided at the BAS workstation is useful information for operations and also the regional energy branch office. Here in the regional office, we can use the central plant kW per ton value as a starting point for remote energy audit of the building. I mean, it's a window into why the building's EUI may be higher than expected. So prior to demand flow, we simply didn't have this level of detailed information available via the BAS for troubleshooting.
Thanks, Mark. And John, if you wanted to provide your feedback from Region 3.
Yes, I'm John Teagan. I'm the energy guy from Region 3. We actually installed one. I just have a couple of brief slides to discuss. Basically, my second slide will be a screenshot of the of our dashboard from when we put in the Siemens demand flow. And while it's a little bit hard to read, you can see where we have the chiller, the KW information, and all the things we're monitoring, and we are able to really dive down and get a good look at how the whole plant is performing. We installed at the VA, which includes a data center, but we did not do the data center side, and we installed over a Siemens BAS, which is over a trained chiller system that was previously used as an ice plant, but we were unable to really run the ice plant because the operating profile of the building went from a single shift operation to 2.5 shift operation 6 days a week. So there was a lot of dynamics involved in what we were doing. If we go back to the previous slide, please, Andrea. Basically, our takeaways were we were able to buy this technology via our O&M, and that made the installation of this. The O&M already had a relationship with his subcontractor, was Siemens, so that made the transfer of this technology much easier, in our opinion, and relatively seamless from GSA's point of view. Key point was to make sure that the vendor trained the operators pretty closely in how the system worked. When we first started to bring it online, the operators were very concerned with whether or not it was working properly, especially as conditions changed into a more a condition which was closer to design operation. When that happens, the savings from this equipment is relatively small, if at all. So you need to really make sure the operators understand and know the basics of how it's running. I mean, as Ron Underhill stated, the algorithm is very complicated, and there's a lot involved there. But they need to know anything that impacts condenser water temperature is going to ripple through and really impact the way the savings is being made, is being achieved. So that's basically what I have to share. The operators like it. It's not so complicated they can't run it. It actually engages the operators in the more efficient operation of the plant, I've found. So we've had good success with this.
Thanks, John. So it looks like it's time for the Q&A, and I noticed in the chat section we got some meaty ones there towards the end. So I think I'll start with Jesse's question. I'm hoping, Ron, you could help answer these. But Jesse Dean asked, with this technology, is it normal protocol to install VFDs on primary pumps? And it's several layered questions. Should a site consider converting the existing system to a variable primary versus installing VFDs on both primary or secondary pumps, et cetera? And maybe, Ron, if you could start, at minimum, if you would share at minimum what level of VFDs are required in the system, because I remember it was kind of a layering that, you know.
Mike, it looks like Ron had gotten bumped off the call. He's just joining again, so he'll be back with us shortly.
Okay. I don't know, Mark, if you can answer that at all, or what you experienced, but what I recall was that you needed VFDs on the pumping system, but definitely not on the chillers, is what I recall.
Yeah, I mean, we did not, you know, these are constant speed chillers. We did not have that, but yeah, my understanding is that on both pumping loops, I mean, if you have both primary and secondary on both of those, and then on the condenser water as well. But I know it's a different configuration when you've got a variable primary, and that's a whole different probably arrangement. I'm assuming that the algorithms would be adjusted for that. Those are such common systems these days.
They don't need VFDs on the chillers, but there's pretty much VFDs on everything else.
And as Ron shared, I think some of the cost, and Mark, you can echo this, but some of the cost of the installation of Montgomery was installing its VFDs, but yet, kind of in a holistic sense, the combination of installing the VFDs and the demand flow collectively, you know, gave the savings that were shared. And of course, you should and could consider installing a chilled water optimization system on a building that already has VFDs, as has been described, but of course your savings likely would be less, but so would your installation costs.
This is Scott Johnson.
Go ahead, Scott.
Yeah, they unmuted me so I could contribute to some of those answers. I'm actually with Siemens and part of the demand flow team. And a simple answer on VFDs is we take advantage of what's already there, and we'll add VFDs to your cooling tower fans, your condenser pumps, your primary pumps, or your secondary pumps if they're not present already. We do not require VFDs on the chillers. If they're there, we'll take advantage of them, but you do not need to add them, and the ROI to add them to an existing project is not attractive, so it's not done for existing sites. Related to changing to a variable primary, we don't go that direction. There was a question on physically changing a primary secondary plant to a variable primary. You could choose to do that. We find it more cost effective to add the VFDs on the primary pump, and we control it to a virtual variable primary by synchronizing the pressures and limiting the bypass in your bridge in the central plant. So hope that helps clarify some of those questions.
Thanks, Scott. And let's see. Nicholas had a question. Was chiller lift the same during baseline and post-case comparison?
I'll try to answer that. We didn't take a look at chiller lift as far as condenser evaporator pressures. That was not part of our data set that we looked at. I don't know if Mark can answer that.
Mark, I don't know if you're on mute.
What's that? A question on lift? No, I don't have anything on that.
Okay.
We don't have. I don't have the before and after. I'm wondering if Ron's got that. Is that mentioned in the report that's on the site?
No, we don't.
Maybe a part of what we present. No.
This is Scott Johnson. I can add some information if desired.
Please do.
I've read that report. I don't recall them measuring the lift on the chillers. But one of the keys to our patent is how we manage that lift. And we optimize the lift based upon the load conditions and what we can get from the weather conditions. So you're going to get reduced lift while we still are able to deliver what the system needs. So that is one of the areas that we're very effective on bringing savings to this system. And we do it in a manner that we maintain the chiller's operations, as was noted in the Montgomery site. We're able to operate those chillers at the lower load conditions and successfully keep them online.
Thanks, Scott. And then Nicholas had a question, were the savings presented extrapolated from the period compared over an entire year, or was an 8,760 analysis, I don't know what that is, analysis completed and compared to actual measured data? If not, was this time period? What was the time period that was used?
That was based on an entire year.
I'm sorry, an entire year?
Yes.
Okay, thanks. And then Jesse had another question. Also, normally VFDs are not installed on condenser water pumps since those are open loop pumping systems. Can you also touch on why VFDs were installed on the condenser pumps?
Well, I'll start. I mean, I think Scott alluded to it again earlier. Yeah, you're right. They're probably not normally installed, but I think what the technology is trying to do is optimize the pressure and the lift, and that ends up resulting in controlling the flow rate. So it's a synchronized dance, if you will, but that's in my limited knowledge of the technology. Scott might have to address that further.
I think you did a pretty good job. It is unique that most sites we go to do not have VFDs on the condenser pumps. So it's a common scope item that we will add. But it is a key to what we're doing. We're varying the flow on both sides of the chiller and maintaining the lift it needs based upon the load conditions and what we can get from the cooling towers, ultimately based upon weather conditions. So it is a better way to operate your system, and it's well worth the investment to install it with what we're doing.
I'll throw out a crude analogy. Most people are familiar with constant volume air handlers. Most people are familiar with converting those to VAV, and they recognize the savings at the fan. So I think what Siemens is saying is we recognize these chill water plants are constant volume at the pumps, maybe even at the towers if the fans are constant speed or two speed. And there's some opportunity here if we apply some technology to vary those flow rates. But I think it has to be, has to be monitored and measured carefully.
And then another question, don't you still need the bypass to ensure minimum chilled water flow through operational chillers?
And yeah, I'll speak to that.
This is Scott.
Go ahead, Scott.
We can both, I'll make my pass at it and please add to it. Yes, you do need the minimum flows, and those are maintained and monitored in the system. So that does not get eliminated. So that flexibility is in there when those conditions occur.
And I meant to add that the example drawing on the slide that showed the plant did not show a bypass valve. It should have, so I apologize for that omission.
And then Nicholas, I was just going to say, Nicholas, you beat me to the punch. So Nicholas asked a question, does this platform work on non-Siemens BAS? And Scott, I know you answered this question on email, so I may throw this at you again.
Yes, any system that has open communications, most typical are BACnet, Modbus. We do work on some PLC systems, but I don't think you would find that in too many of your GSA sites. You're probably going to find other vendors in the BAS market. And we've got this installed on other federal sites with Tritium systems. We got it installed with Johnson systems. There's not a limitation from the technology standpoint. The limitation is, can the control systems talk? It takes advantage of your current investment. It's not so on sites that this is put on that has another vendor, we will just add a controller so we can communicate with the system that's there and provide the set points that are needed to the system that's there. So it augments your current investment. And as long as those systems can communicate, this technology can be applied.
Thanks, Scott. And I think I see one last question. Jeff asked, what do you normally experience as the minimum % chilled water flow requirement for the chillers?
Well, we get that part load data from the chiller manufacturer. So usually, 30% is, a cutoff point, but it varies based upon how that chiller was put together with the bundle of tubes for the condenser and evaporator, and we customize that and hard code that into every one of our solutions.
So it's really more of a manufacturer limitation, not a limitation of your system.
Correct.
Okay.
We just understand that. That's part of what we do is understand what that chiller's performance is.
Okay.
This is Ron.
Andrea, do you see any other questions? I don't.
This is Ron. I have a question. Or a comment. Maybe a comment would be better. Can you hear me okay, Mike?
Yes.
Okay. And one of the things that I'm curious is, one of the assumptions that everyone might go into this is that the plant, the chill water system, the chiller, condenser barrels, evaporator barrels, everything's properly maintained. And I guess for our Siemens friend, what does Siemens, do they look at those type of situations to see if the towers and the equipment has been properly maintained, strainers, et cetera? Or would that be part of your analysis up front? Say, you know what, we can apply the technology, but we also need to take a look at how the equipment's been maintained and make.
Yes, that's part of our analysis.
Okay.
Sorry, please finish.
No,
Sorry.
I just wanted to make sure everyone understood that again, because you guys are taking the flow rates down to a lower level. Some people get concerned, from a risk standpoint, but I think it's important to recognize that you have to also have the proper maintenance on those systems.
We don't find perfect systems. It just doesn't exist. This is the real world, and there's some degree of degradation on every site. You don't have to have a perfect system, but we do. That's part of our upfront assessment, is understanding the issues and limitations that are there and help identify the impactful ones. And we're putting a savings number on it, so it's important for us to understand that so we can actually deliver to not the theoretical opportunity, but the real opportunity.
Thank you.
So our information is based upon how the site's performing, and commonly, you can find issues with the cooling tower. You can find chillers that aren't charged properly, but we can help identify that and bring the right attention to resolve. Another way of looking at plant operations, most sites are overdriving their system. They're flooding your facility with energy to overcome the shortcomings, and that is actually a risky way to operate because you cannot see the failures that are, the equipment that's struggling. So as we lower that, use the analogy of lowering the lake level, you're just going to see these rocks, and we can get to the root cause of some of the weaknesses in your system, and you can decide if you want to address those. So we help find the weaknesses in the system, which can be give you a better uptime in performance.
Okay, thanks. And then I misrepresented Jeff's question. His question actually was about % condenser water flow requirements related to condenser. Are there specific minimum condenser water flow requirements?
That also gets back to the same data set. The chiller manufacturer has part load submittals that define at part loads what the minimum flow is on the condenser and the minimum flow on the evaporator. Actually, the minimum evaporator flow can be more critical because the potential of freezing tubes, but we look at both of those, and we quite often, if it's an older chiller, we're going to improve the instrumentation that measures that flow. If it's a paddle switch, we'll probably improve that to a more modern technology to more accurately measure that flow, so we can bring more resilience to the system.
Okay, thanks. And then what I think is going to be a last question, in a Siemens BAS system, are these algorithms leveraged with existing controllers or an additional controller?
95% of what we do is on existing controllers. We do add one additional controller that would have roughly 5% of the activity in that. So that would be the same analogy, whether it's Siemens or somebody else's system.
Okay. Whenever I say last question, there's another one that pops up. Nicholas asks, any risk underflowing the towers?
Yes, you have to understand that. That's part of what we're taking a look at is the minimum flow requirements on the tower. Potentially, if it makes sense, we look at adding little flow kits to the towers. You have to maintain the media saturation so you don't dry and scale the towers, and we understand that. That's part of what we engineer into the solution.
Okay, thank you. And my last statement wasn't to discourage questions. I don't see any more questions. Are there any out there that someone's just not yet asked?
I have one question. This is Ron again for Siemens. When you look at a site, whether it's GSA or otherwise, what's the how do you guys approach supporting those sites? Do you have a long-term service thing, or because it's an investment for the sites? How do you recommend that they evaluate that? And then the second add-on question to that would be if their BAS is upgraded, what does that look like to you and to the owner as far as the things that have to be reconfigured, rediscovered? What does that process look like?
Well, I'll start with your last question because it's pretty straightforward. BAS upgrades don't compromise the solution that you've already got. I can't think of a scenario. Excuse me, let me turn off this call coming here. So that's not a limiting factor. But to your first question, sorry, I got distracted by the phone. What was the first question again? Can you give it to me again?
Yeah. The first question is just what do you see as a long-term relationship as far as support that sites might want to consider?
First of all, you own this solution. You do not have to have a service agreement going forward to maintain it. It's a solution that is owned, and so there's not a hard, firm requirement to get a service agreement. But we do encourage a service agreement, and over time, we've had this solution in the market for about 13 years. We've put a lot more effort in the recent months and years about building the service capabilities around this, having a remote service team that can remotely support where customers allow that. There's a strong benefit to provide some level of operator coaching and fault diagnostics. We can either do that locally or remotely. So it's whatever works for the customer, but it's become a more consistent need and request to help customers maintain solutions going forward over multiple years.
Thank you.
And John Teagan, I think you've had experience with that, and how have you managed that in your region? John,
I'm sorry, I had to get off mute.
I know.
We're still working through it. We're looking to see that this is at a location that's migrating very shortly, so I'll know more relatively quickly. It's a challenge.
Any other questions out there?
Yes, it looks like we have one from Charlie we haven't copied over yet.
I'm sorry, is that on the form? There we go. Did you measure the impact on makeup water?
The national lab did not have that data. I'm assuming it may have gone down, but I think Mark Moody or the site staff would have to address that.
Mike, no, we don't have that sub-metered in that way. I mean, if somebody was interested, we'd have to, I think, look at the tonnage saved, and there are ways to convert tons to make up water over time, but we don't have that number handy.
Okay, thanks.
We did notice a slight decrease in makeup water, but and this is a building we monitor water in very closely. So we think there's a slight decrease there, but we haven't put our hands on the actual numbers yet as well.
This is Scott Johnson from Siemens, and we see the same thing where we actually get a reduction in the makeup water. And to our detriment, we haven't focused on that to quantify it. There's multiple factors, but it's mainly driven by reduced tonnage. We're using less energy at the chillers, and we're more effectively distributing water for the facility, and it does result in some reduced water usage at the towers. I'd say in the 5 to 10% range, but we don't have hard data to back that up.
Right. Any other questions? As Andrea has shown, I think this is a wrap. Thank you, everyone, for joining us.